are starting our afternoon session. This introduction is not going to be like others, just because this speaker is not like others. He is the artist who designed this cartoon. And now you can have different thoughts about it. So you can think it's just a realistic depiction of scientists at work, sort of in a tradition of Vermeer's Astronomer. You were supposed to laugh here. Thank you. Or you can think that this is kind of a critique, because if you see between one blackboard to the other, it should be taking about 20, 30 years. So maybe it's a critique, a lament that it takes so long. Or you can think of it as a suggestion that we should just shrink the time between these blackboards. So, as you wish. Robbert was among the people who metaphorically brought another blackboard into his office. So not only really modern, today's mathematics is used, the work done is also directly and seriously impacts mathematics. And he is also one of the best explainers of physics to mathematicians and mathematics to physicists. And not just that, he is probably also the closest our field has to a public intellectual. Not only he explains the importance of science to general public, but also he influences and implements scientific policies, such as being the president of Dutch Academy of Sciences or currently the director of Institute of Advanced Studies. So it's our pleasure to have Robbert for this afternoon.
Thank you. And a great pleasure, thank you. I must say, actually, this cartoon was on the cover of two very thick volumes of a workshop we had in the 1990s at the Institute for Advanced Study. And I was very happy that I actually got a citation to the cover. So I've won, this actually has one citation, I think in a paper by Fadeev. Let me just start this. So I want to talk quite generally about the interaction between math and physics, and I will do this. First, I will have some more general commands, and then I'll move to some more kind of specific examples. But I really want to kind of sketch to you kind of the big picture, particular what we kind of mean by quantum geometry and the interaction between mathematics and physics that kind of brings that new field that, of course, we in many ways is a large umbrella under which a large part of stringy mathematics, as we had last week, belongs, but I think many other kind of intellectual developments. So there's, of course, lots of things to be said about mathematics and physics. I think it's the favorite topic for all of us. You know, I noticed that quite in general, it's a dangerous subject. Undoubtedly, at one of the late night sessions, you have been telling jokes about mathematicians and physicists. And I want to share one with you, which is my favorite. I always like to tell it here because actually Alan Kohn came with that joke. So Alan had the following metaphor. He said, you know, in his idea, it was a physicist that actually was carrying a heavy bag of laundry and was going to the small village to find a place to do his laundry. And then certainly he saw a shop, and the shop had a big sign outside saying laundrette, but also said cafe, it said hotel, it said restaurant, everything. So we go there, and then of course the shop is run by a mathematician, and he asks, can I do my laundry here? No, you cannot. But wait a moment, there was this big sign. Well, the only thing we sell is advertisement signs. And so that's in some sense the one particular perspective that I would say traditional physicists have on mathematics. Now we are actually here in that current kind of frame of thinking, but some physicists feel very strongly, like Odysseus, they have to tie themselves to the ship, not to be kind of seduced by the sirens of mathematics, because it's so tempting to go in a mathematical world. And you know, all this joke as kind of reality, as a physical reality, as a first order approximation to mathematics. And but just, you know, go and take a little bit more, a more historical point of view. This is this famous quote of Galileo, who used the metaphor of reading a book as learning about nature, of course, very appropriate at that time in the history of science and scholarship. And he has this wonderful phrase that the book is written in the language of mathematics, and in that time, mathematics also Euclidean geometry to a large extent, so triangles, circles, and other geometrical figures, and without these, you're wandering around in a dark labyrinth. And I think that's something that we feel very strongly. My other favorite quotation is this one from Richard Feynman. For those who do not know mathematics, it's difficult to get across a real feeling to the beauty, the deepest beauty of nature. If you want to learn it, you have to understand the language that he speaks in. And Feynman, I just have to add to it, he has many other quotations about mathematics. This is kind of the late night version. If all mathematics disappeared today, physics would set back exactly 1 week. I guess that's why we have a 1 week conference, just to catch up. And I always thought this was a really smart put down until a rather famous mathematician, I can actually share with you who it was actually Michael Atiyah, said, well, the response is that was the week that God created the world. So I think it's a beautiful, beautiful phrase. Of course, I mean, it's a very deep philosophical theme about how the experience of nature and realities influences mathematics. And of course, we can say that, the classical world, that is to say the world that we as human beings observe, from everyday objects to the celestial bodies, led clearly through Newton and others to the development of calculus. And we've seen that classical mechanics and calculus and dynamical systems kind of were created at the same time. And there's this wonderful phrase, I think it's actually from Lagrange, who said that Newton must have been the happiest person in the history of the world, because only one person can be the first to discover that there is actually a system in the world. In our languages, that there is a mathematical framework to understand the world. And the theme about this day and my lecture is that this should hold true even more stronger for the real description of nature, which is in the fundamental sense, of course, quantum mechanical. And so one thing I think what we are doing in mathematics, we are absorbing the natural frame of quantum theory in a way to understand the world and somehow shed a new light on what is mathematics. And it's very different. There's a much more probabilistic approach, very different concepts. By definition, the quantum world is foreign to our everyday intuition. And so perhaps the grand dream is that just as Newton developed calculus, we, the present generation, should invent or discover a new language which is somehow quantum mathematics. And it would have some property. There would be a deformation parameter, Planck's constant, h bar, and if you send it to 0, you go back to the classical world. That's at least one possible approach. Now, this is kind of question of framing and what's the best way to understand. And this is a wonderful paper by Bill Thurston that I really recommend on proof and progress. And he asked this question. He asked the question, take, for instance, a very simple mathematical concept. Take the derivative. What is the best way to understand the derivative of a function? And he said, well, there are many ways. And he starts with like definition 1, and he writes down the formal definition. And if you look at the paper, you see that there's a mistake in that definition. So the epsilon delta definition. But he said there are others. You can think about it as rate, as a velocity. If you do that, you immediately realize that the derivative can be a vector-valued object, can point in a certain direction. You can think of it as a slope, as a tangent. Then it's actually easy to think about a function of more than one variable, or the whole infinitesimal language, or think about discrete steps. Then you can actually move the concept of a derivative to discrete mathematics. Or you can do it symbolically and move to completely different realms of algebra. Or think of it as the linear approximation, or think of it as looking at through a microscope. And then at some point he says, well, the definition 37, which is some Lagrangian section of some cotangent, is at some point that's the definition I needed. Well, I think his point is that there is not a definition, a best definition of a derivative. A very powerful mathematical concepts can be brought to life by all these different facets. And actually they reflect the natural environment in which derivatives operate. And so I think we're trying to do something similar. There's another element, but just a little bit jokingly, if you have mathematical equations, they typically take this form, I'm just joking, A equals B, and I want to kind of make a point as a symbol there, which is usually not getting emphasized, which is the equal sign. Now, philosophers actually have some kind of theory about this, and they call this kind of Clinton's principle, because that's actually going back to the 1990s, although it's come back to the present day. At some point, Bill Clinton had a statement about that there is no appropriate relation, I think. So there was a definition. What is. What do we mean if we write the equal sign? And I think in many ways, and I think certainly the equations that come out of physics have this magical property that they are connecting different worlds. A and B are usually in completely different realms. And the most famous equation of something out of physics, equals mc squared, is a wonderful example of this. It's connecting two different physical concepts, energy and mass, that not necessarily are related. And so the equation does more than just state a certain mathematical fact. It's actually connecting different worlds. And you can go and look at your favorite mathematical equations and see whether they have that property. I think many of them have. There's another element that, if you think about mathematics, we talk about the unity of mathematics, but we are like this kind of hyperactive butchers that are, we remember when we had an introduction at the University of Amsterdam for freshman students, and somebody showed the American Mathematical Society classification as the first slide. They said, well, this is mathematics, A few hundred different certain students were kind of frightened, I guess, from that. So the nice thing is that if you are a physicist, often you don't really care about how these different realms of math has been numbered and described. So in many ways, in a funny way, physics is a good way to approach the unity of mathematics. Because in some sense, the applications in physics cut across disciplines, mathematical disciplines, in some very kind of elegant way. So I think that's another kind of benefit that we see. There's also just showing here the seal of the Institute for Advanced Study. When the Institute was created in 1930, the director thought not so much about recruiting faculty or buildings, but the first thing he did was actually design a seal, had a seal designed, and he had the motto, truth and beauty. And you could say there's a certain tension there too, which in some sense captures the physics and mathematics discussion. And so there are some quotes I want to share with you. There's this famous one of Hermann Weyl about try to unite the true with the beautiful, but when I had to choose one or the other, I usually chose the beautiful. I would say kind of perhaps the mathematical point of view. Paul Dirac famously said that it's more important for equations to be beautiful than to have them fit experiments, and he has, of course, wonderful examples where he actually was right. And then there's the opposite point of view that I think was very well put by John Wheeler. It's actually quite a deep statement. Every law of physics pushed to the extreme will be found to be statistical and approximate, not mathematically perfect and precise. And his point was, if you want to have a mathematical result that will stand through time, it better have a certain plasticity. It has a certain ability to change or add details, because if it's the final word, it actually will break or it will stand. And often, I think, in the confrontation with reality, it might break. There's this famous quote, Francis Crick, any theory that we can account for all the facts is wrong because some of the facts are always wrong. We don't know with 100% certainty what the world is that we try to describe with our mathematical formulas. So this is like philosophical point, where do we find mathematical beauty? Anywhere. And you could say in some sense there's this kind of argument that, if you look at the world in terms of energy scales, or length scales from the large to the very small, you can somehow see that like complexity is really in the middle. And simplicity, and probably also mathematical simplicity, you might find at two ends of that spectrum, at the very, very small, of the very, very large. That is in terms of particle physics or cosmology. And there are basically two ways in which these mathematical structures can arise. I will say a few words about it. They can arise through reduction, namely going to the very, very building blocks of nature, or they can arise through emergence, that is to say, the collective behavior of many, many different building blocks, where, again, life simplifies, or mathematics might simplify. So, in some sense, that does capture the essence of this whole discussion about quantum geometry. And so think about two ways in which we see this. For instance, in the world around us, to a large extent, it's light interacting with matter. And we know it's very complicated, but at very small scales, we have quantum electrodynamics, a very beautiful, elegant, simple quantum field theory that describes these processes basically in terms of two particles, a photon and an electron, interacting through very simple Feynman rules. On the other hand, if you take a glass of water, you have a very complicated system, many, 10 to the 24 H2O molecules. If you go to very large distance scales, then we know that actually simple laws emerge. Thermodynamics, the Navier-Stokes equations, come out. So in condensed matter, you would typically say that the simplicity and the mathematical elegance arises at a very large. Now, in many ways, this is reflected, I think, in our topic. So for the purpose of this lecture, I want to kind of just, and following some of the previous lectures, Hiroshi made the same point. You can think of mathematics roughly as two parts, the geometry and algebra. Algebra is basically the left side of our brain, is the part that thinks in terms of algorithms, in terms of particular mathematical logic, seeing it as a path of steps. And geometry as being the right half of our brain, in the way in which we spatially orient, walk around, think in terms of shapes and forms. And these two parts are in some sense reflected in the two ends of the natural world. So we see geometry, namely in terms of general relativity, describing the very large, and algebra in terms of quantum mechanics, describing the very small. So you can think of some sense in a very complex world, and algebra and geometry are capturing the two ends. Thinking about what we will be describing is in some sense the equivalent, the mathematical equivalent of these two processes by which we kind of reduce or emerge to structure. So as we'll see, is the whole idea of quantization is taking a geometrical object that is something from the realm of classical physics into the world of algebra. And so, for instance, certain processes which you would describe in terms of classical mechanics as certain trajectories would have probabilities associated to it. So there's some rule that takes an object in the classical world and associates to it, for instance, a complex number as the probability amplitude. The opposite, I will try to say a few words about it, is something much less known in mathematics, and we have seen it as incredibly important in quantum gravity, is the opposite effect. The opposite, in some sense, of quantization. I mean, taking an algebraic structure and seeing how geometry emerges from it. And I think the synthesis, so this is the thesis and the antithesis, the synthesis of my point, and I think the general point of where we are in this whole development, is that through quantum geometry, whatever it is, and certainly string theory is one approach to it, is actually combining the two, saying, well, that actually should be a symmetric situation. In the same way as we can quantize and get algebraic structures, we can kind of get geometrical structures out of algebra. And so we are looking in some sense a framework that's capturing both and in kind of in an equal fashion. Now, just a little bit of an historical line. So this is something that Hiroshi already showed this morning briefly. I'd like to joke this Plato's standard model. These were the 5 Platonic solids that had to cover for the 4 elements, together with the 5th element, the dodecahedron in Plato's view was the 5th element that described the perfect world outside planet Earth. And it's kind of interesting. You can see this dodecahedron at many different places. My favorite one is this one. It's actually hanging in the great old meeting hall of the Dutch Parliament in The Hague. And I saw this picture in a newspaper, and then there was a commentary. Said, well, it's very appropriate of this time. Well, isn't it a little bit kind of low class for the Dutch to have a huge soccer ball in their parliament, not being aware of more than 2,000 years of metaphysical thinking, a factor or two of these. So Kepler, I mentioned Kepler, and I want to use this metaphor to ask the question, what is the kind of mathematics that we're looking for? Kepler was very much enthralled by these Platonic solids and everything, and Now, there's this wonderful, I hope you know this, there's this wonderful little book he wrote about basically applying mathematics to the real world. It's his book on the snowflake. In fact, he gave this when he wasn't paid for some time, and he had to, and you know, the snowflake is kind of rhyming in Latin on the word nothing. And so what he said in that book also, well, he wasn't paid, so he had to give a Christmas present gift to his benefactor, and he said, well, if you have nothing and you receive nothing, what can you give but nothing? Which was the snowflake. But in some sense, what he was describing is the idea of symmetry in physics, which was, I think, a great gift. So I mention this because of what Hiroshi showed, Kepler's famous first cosmology, his attempt to describe the 6 orbits of the then known planets in terms of stacking the Platonic solids. And I think it's a beautiful metaphor because we all laugh about this effort to describe the physical world, and we know that's not the way it's described. In fact, Kepler's first law is describing the orbits of the planets observationally as being conic sections, ellipses. And there's this wonderful quote in his work, in his diary, I think, where he said that he is, by introducing these ellipses, he's bringing a horse cart of manure into science because he feels he's really breaking the perfect symmetry of the world. And this is like kind of an ugly shape. It has a modulus, so it's no longer be determined by a simple mathematical arguments. Of course, now we know there's a very general theory about these orbits, and we say it's absolutely beautiful, and when we teach first-year students, it's one of the great applications of mathematical physics to find these orbits. So you might say that, you know, Kepler was right in finding mathematics to describe these planetary orbits, but he was picking the wrong mathematics. So you can kind of ask, you know, if you're looking for mathematical objects that would describe the real world, we find them beautiful, what kind of beauty are we looking for? Are we things which are like differential equations or dynamical systems, very general concepts, or are we looking at exceptional structures like the Platonic solids, or, you know, special manifolds? And I think honestly we are confused about this. If you look at the world, on the one hand we know there are general laws. On the other hand, there's a very specific physical model that we want to find, the physical model of the elementary particles, etc. So I think even string theories are of two minds, in some sense, what the kind of mathematical beauty we try to find. So for the purpose of this lecture, I want to kind of think of the various kind of stages and bring you with it. So I find it helpful to think in the following way. So kind of stage 1 is kind of classical mechanics. And classical mechanics is describing the world in terms of certain specific processes. So you typically minimize some action function. And you can think of it as the straight line from A to B, or it's geodesic in a curved space. And so there's a lot of mathematics that goes along with that. Clearly all of calculus, dynamical systems, a large part of geometry. If we move up to quantum mechanics, one way to think about quantum mechanics is as a history of all possible paths with a certain probability amplitude associated to it. So it's a sum of histories, and which by itself is already a very powerful concept because it tells you shouldn't look at one particular object, but you should look at the grand total of it. And I think that's something that we knew in certain branches of mathematics very well, like combinatorics. But I think, you know, through this point of view, large other parts of mathematics, like differential topology, have been influenced by it. So then the third level, in my point of view, would be quantum field theory. It's like second quantization. So in that case, you know, you not only go from A to B, but you can also arrive in C. So particles can be created and annihilated. And it's a study of Feynman diagrams, or in non-perturbatively of quantum fields. And we'll see some of the topics that have been influenced in this last few decades, studying all of that. Then the fourth stage would be string theory, where we kind of replace particles by strings. So it's instead of looking at the movement of points, it's the moving at little loops. So it's studying spaces through the eye of loop spaces. Here are some of the topics in mathematics. And kind of the final stage would be kind of the grand finale, would be to study quantum gravity or branes, where in some sense, you know, it's even more complicated because in all the previous examples, it was about things that were moving inside a fixed space-time manifold. But if the space-time itself is kind of either fluctuating or perhaps even emergent, it's not even clear what the right language is. And that's why we often resort to algebra. And so in some sense, it's very closely related to non-commutative structures and some of the topics that we have been studying and learning about during the conference. So just for practical purposes, pedagogical purposes, let me build up. And so my favorite way to introduce particle physics is always with this kind of, it's just quite remarkable if you look at the things that come out of particle detectors, which looks like a lot of garbage, that actually there is such a beautiful mathematics in it. And one way to understand this, of course, is the whole way of Feynman diagrams. And my favorite way to introduce this is this famous telephone call. John Wheeler, at that point, was advising Richard Feynman. It was in the early 1940s, and he calls him late at night, and Feynman describes this as a Nobel Prize lecture, where Wheeler says, "No, I know why all the electrons have exactly the same property, because there's only one electron in the whole universe." And he had this beautiful idea. If you think of a particle moving in space-time, that's not just moving up, but up and down, is allowed to go back in time. Basically have an arbitrary trajectory in space-time. And you slice it at different time sections, you might see many, many particles coming up and down, and clearly they have the same property. I think it's one of the most brilliant and fundamental ideas in physics that, and it's now totally absorbed in our thinking about quantum mechanics, but it was a very non-trivial step to take. And I always find it very moving. This is the first page of the notebook of Feynman, where he actually is for the first time trying to send these particles back in time. Where you see them, he's making little loops, he sends them back. And you just notice that actually the rules of quantum mechanics are behaving in the appropriate way, and this is the way to reproduce the standard quantum field theory language. And so it's a very powerful way to describe particle physics in terms of these Feynman diagrams. Now, and it's kind of remarkable, this is the Lagrangian of the standard model as written down in full gory details. Actually, it's in one of the textbooks of Martinus Veldman, one of the famous Dutch Nobel laureates. And of course, on the right-hand side, you find the diagrams, which in some sense looks much more nicer or something than these used formulas. So the remarkable thing, of course, that we learned in particle physics is that there is a very simple standard model of particle physics at this point, including the Higgs particle, which, if you want, can, with elegant notation, it can fit on one line. All the objects that are in that equation are natural geometrical objects. And it's kind of interesting if you these conferences and these discussions about the interaction between math and physics, you can somehow say, when did it start? Do we have kind of a starting point of that development? And I would say it was something in the 1970s. On the one hand, there's this famous quote by Freeman Dyson from 1972 that was just before the revolution, that he was acutely aware that the marriage between math and physics had ended in divorce. And that was because in the 1960s or something that these were really two different continents, not interacting in many meaningful ways. And just around that time, the dialogue started. And for instance, this wonderful seminar that was run at Stony Brook, where the physicist Yang and the mathematician Simons were basically comparing notes. And I always like this kind of table that came out of that seminar, which is, on the left-hand side, it has the physical notions. On the right-hand side, it has the mathematical notions, and it's almost like a Rosetta Stone. You see the physical and the mathematical quantities could be related, and that was a very non-trivial step to take in that time. Now we think of this as all particular obvious, and I like the fact that there's a question mark here. The electric source wasn't yet here in the language of bundles, and those of us who are active in that field know, well, that's very nice, because this is about introducing singularities and dislocations and branes and everything. So it was a wonderful research project to it's great if you get a dictionary with a question mark, because you know that there's probably a very good answer to it. So if you want to think, what is the way to phrase all of that? Again, I would say the general concept is the concept of symmetry. And so this is one way to think about it. If you think in the simplest form, like for instance for the strong force, it's a gauge theory. So it has particles, quarks, come in 3 different colors. That is to say, you think of a particle not as a point in space-time, but it's a point which is enriched by a vector in an abstract 3-dimensional space that basically tells you what a particular color is. And in some sense, this color is there, that color vector is there everywhere in space-time. And in fact, it can not only move in a collective fashion, but it can move like independently. So there's a huge symmetry group, which is the gauge symmetry group, that allows you to rotate that color vector at every point. And in some kind of vague intuitive form, you can think as the fields as kind of the collective motion in that kind of sea of little arrows. Now, if you bring gauge theories, and I will come back to that, to the world of quantum mechanics, you will have to describe it in terms of particle physics. So, particles, quarks can have a certain color, and they can change color, like a red quark can turn into a green. And the way it does so is by this interchanging, now not of a photon, but a gluon. And these gluons, which are color-changing objects, by definition, they carry 2 colors. So, for instance, this would be a red-green gluon. And you can see there's like a matrix of these gluons. So there's a very natural n-by-n matrix, 3 by 3 in the case of the strong interaction, but in general gauge theory, thinking about it in the quantum mechanical world, you would immediately get these kind of matrices kind of for free. So there's like a non-abelian structure deeply hidden in non-abelian gates, in these kind of gauge theories. Now, the way this, I think, so I want to kind of show this because it was like basically one of the first strong applications of these ideas in mathematics. Now, in quantum mechanics, you not have just particles not go straight through, they not go up and down, but they can even split, like you can have Feynman diagrams like this, or in fact you can have particles like this. This is a process where, from a physical point of view, it's a virtual pair of particles that's created and then annihilated. Another way to think about it, it's just a particle that goes up and down in space-time, which is a closed loop. And it's actually processes like this that describe the vacuum state of the diagram. So we call this vacuum diagrams. They are describing physical processes in the absence of real particles. So they're just describing the quantum vacuum. And so you can think of this as like a sea where particles come out all the time. And the great way, I think this idea found its way into mathematics, which I think was like almost exhibit A of this new era of math physics interaction, was in knot theory. So if you think about knots, you can think of these as physically, some want to classify all possible knots, but the physical point of view as well, you can think of these knots as kind of trajectories of particles moving in space-time. So think of this just as a vacuum diagram. So it's a particle that, it's actually a bunch. If you think of slice this, it's a 2 + 1 dimensional space-time. If you slice it, you will see a complicated process where particles appear out of nothing, move around, and then disappear again. And according to the rules of physics, any such process in any physical theory should give a quantum amplitude. So there should be a number associated to it. And this is exactly what Chern-Simons theory does. So it computes quantum invariance. So you can think of this as the processes that are describing, the numbers that are describing the probabilities of these specific processes. But I think in some sense the lesson was much more general. The lesson was that to these kind of geometrical objects, knots, and all their cousins, tangles, and you can move in different dimensions. So this was in some sense can generalize in all possible directions. Should come out of it certain kind of algebraic objects, probability amplitudes for physical processes. But you can generalize in other ways, and there are knot invariants where the value is actually it's the things that come out are integers. They could be dimensions of vector spaces related to this program of categorification that Android talked about. So in many ways, this is an example that can be generalized in many, many different directions and really captures, I think, for me, that movement from geometry to space-time, from geometry to algebra. In fact, it's also related to this kind of question about what a quantum field theory is. Now, from a naive point of view, a quantum field theory is something where you have a kind of a space-time manifold and you have some local field theory. So I think of this almost like a bucket of paint. And you put these quantum variables on the manifold and you get something. You get like a partition function. And there are many ways then to study these theories. I think so we've learned that, you can try to do it in terms of local operators and Feynman diagrams. You can do it by looking at these theories on very different sets of manifolds and trying to probe the quantum field theory by cutting and pasting that specific piece of space-time. Let's see what's happening here. But there are really bizarre things happening. And I think so, if you ask from a mathematical point of view, do we understand quantum field theories? I think the briefest and most honest answer is no. I don't think we really understand what a quantum field theory is. For instance, there is this wonderful example of duality. You can have two classical field theories. So a set of Feynman diagrams, say, F and F star. And if you think of them as quantum field theories, they certainly are part of a large space, a moduli space of quantum field theories, where they both appear as classical limits. So you can have two kinds of classical limits. There's one limit where h bar is tend to 0, and then there's another parameter that behaves just like h bar at another end of this kind of large landscape of quantum field theories, where a dual field theory is emerging. So that could be a field theory with a different gauge group, different representation, etc. So it's almost like I always think of this space of quantum field theories as a large ocean. And I think now we are like and the classical world is basically the coastline of the ocean. And what we're doing, we're just trying to explore this very close to the coast. So we have some ideas to this immediate neighborhood. But it's very difficult to go across the ocean all the way to other ends. And I think in general, we have no idea. In fact, that ocean might be very complicated. It might have lots of separate lakes, and there might be lots of bad things going on, singularities, etc. We know that space is out there, but I think we have no way in which we have to describe it. Now, let's go to the next stage. We go to string theory. We have a very similar picture. Point particles are replaced by little loops. In fact, it's very natural to distinguish now two parameters, which usually are labeled the string length, which is the fact that measures the loopiness, so to say, of, so that's the parameter that shrinks the string to a point particle. And then it's what's called the string coupling constant, but really plays the role of h bar. And it's kind of, one way to think about it is that there are like various phases. If both are small, we're talking about particles. If we put the string length parameter up, we generalize from particles to strings. If we basically put the coupling constant large, we go from particles to fields. And if you have both, you get into this much more complicated regime that I think we vaguely describe here as brain theory, but it's much more open. And so one way to think about this is that you have classical geometry, then you have something like loopy geometry or geometry defined by going through loop spaces. And then there's the real quantum geometry where quantum effects are all over. Now, there are many applications. I want to share with you one, perhaps the most famous one, the mirror symmetry example. For those of you who haven't seen that before, it's a very powerful application in mathematics. It was discovered a long time ago. And I think, again, it kind of triggered a wave of developments in all possible directions. The original example was the quintic-Calabi-Yau threefold, this particular geometry, and counting lines on it. So these famous numbers that we now call Gromov-Witten invariants. N of D is counting the number of curves of degree D. So N1 is the number of lines, 2875. Then there's N2, the number of conics. There's N3, the number of cubics. And the remarkable thing was, so this is a very difficult, originally very difficult, still are very difficult calculations to do in algebraic geometry. That kind of string theory or physics was able to kind of produce all of these numbers at once. Because, again, in the spirit of quantum theory, you shouldn't look at these numbers separately. but you see it at the grand total. And the grand total was basically a string partition function. A string that's moving in that Calabi-Yau 3 manifold is basically exploring all the curves of all possible degrees. So there's a quantum amplitude that essentially is computing this kind of generating function of all possible stringy contributions. So the way to think about this is, again, just as a particle was a curve moving in space-time, a string is moving this cylinder if it's just at a very elementary level, which of course we can think of as either two-dimensional real or complex, one-dimensional complex. So it's an algebraic curve. And so we generalize the Feynman diagrams, as Hiroshi mentioned this morning too, into these pair of pens. We're studying Riemann surfaces, maps of Riemann surfaces in a fixed space-time manifold. And they come with a lot of extra benefits. So one thing that strings have is that, different from Feynman diagrams, is that this process which describes the merging or splitting of strings is a very nice, smooth geometry. So string theory comes for free with a multiplication. In Feynman diagrams, you have to determine that. You have to say what are the rules that calculate the contributions of a specific Feynman diagram. In string theory, this kind of comes out of the theory itself. There's a natural application. And then there's this particular branch of string theory, topological string theory, where you don't consider arbitrary maps into the Calabi-Yau, but you restrict to so-called pseudo-holomorphic ones. So where basically it becomes a counting problem, and it's this Gromov-Witten invariance, these n of these, are exactly counting the number of these maps for a fixed degree. So one way to think about it is that string theory is generalizing natural geometrical structures. So for instance, this is a very simple example. If you have 3 planes in a 3-dimensional space, they typically will intersect in a number of points. It's the classical intersection product, which you can also write in terms of differential forms. And string theory, or this kind of perturbative string theory, generalizes this in the following way, that you're not looking at 3 surfaces that intersect necessarily in a point, but it's more that they have a common, there's like a projective curve that intersects all 3 of them. So there's a curve of degree d that goes through all 3 planes, and you can think of this as a deformation of the natural intersection products. And so won't go into details here, but that's part of this whole picture, that quantum structures should be thought of as deformations of the classical things, the classical geometry that we know so well. And again, the big surprise here was that there's apparently a different way to think about geometry. Now, usually we know exactly when 2 spaces, x and x star, are the same or not. But in this kind of string context, these classical geometries could be the limiting cases of a quantum geometry. In this case, would be classified by the space of a certain set of 2-dimensional conformal field theories. And again, there are kind of 2 limits here. So it could be that there are 2 ways to take a classical limit. So you have this big blob of theories, quantum field theories, 2-dimensional quantum field theories, string theories. And there's one way to go to this shore, and you discover geometry X, and you go to this shore to discover geometry X star. So in some sense, I think this is even if you're only interested in the classical story, this is such a powerful result because it shows that there is a relation among objects that we didn't expect and is very deep. And it has had infinite number of ramifications in understanding these geometries. So, and again, there could be very kind of quantum examples which do not have any classical limit, and we should probably also take them into account. In some sense, of course, this whole classification of spaces that was totally driven by string theory was a need to describe these internal dimensions, Calabi-Yau manifolds, and the shape of these spaces then translate into the properties of certain particle physics models. I won't discuss this here, but what it brought is that it was very natural, again, from a physics point of view, not to look at one Calabi-Yau, but look at the grand totality, and then seeing that there are certain patterns, and that's how mirror symmetry basically was found first. That to say, well, there are spaces X and X star that have a natural relation. They actually describe the same kind of physics, although their classical geometry is very, very different. And mere symmetry is just the reflection of that. It basically says if you want to compute these very complicated Gromov-Witten invariants on space X, so counting this number of curves, horribly difficult thing to do, there's a kind of an easy way, quote unquote, by going to the mirror manifold, where the same calculation looks completely different. In that case, it's a period calculation. But basically, it tells you, well, there's one way to understand the left-hand side by going to the right-hand side. But you can't go from left to right just in the world of classical mathematics. You have to kind of go over that bridge of quantum theory. And I think that's so important. That's why we feel it's so important to construct that bridge. Well, the third and final part, I want to say a few words about branes. Well, branes all go back to this crucial point that we know that all the interesting quantum field theories in the real life and also in mathematics, they're gate theories, so they have to do with these matrices of particles, like the 3x3 matrix describing the gluons in the strong force. And there's a wonderful way in which string theory realizes this in terms of branes. So branes are submanifolds in space-time where strings can end. So you have, instead of closed strings, you have open strings. They can end on these branes. And these branes can have a certain multiplicity. That is to say, you can have n of them. And if you pull them apart, these strings can begin at one and end at another. That is to say, as a natural the strings naturally become non-abelian. They take the shape of an n by n matrix. So matrix multiplication is very obvious from brane point of view. And in fact, you can just see that the way these open strings interact is just through matrix multiplication. So you really see, and we knew this from, of course, for a long time, that in string theory, inside string theory, is the whole language and framework of non-abelian gate theories. It's part of it. We knew it was part of it. We knew it was part of it to describe gauge fields, just as we knew that string theory was there to describe geometry and general relativity and gravity. I think only the last decades we have to learn that these two points of view are intimately connected. In fact, they are equivalent. So I want to go back to my key point, is that if there's any topic, grand project that we want to do in mathematics, is kind of unify geometry and algebra in a very meaningful, deep way. So we have to find a language that kind of is bridging these two things. And you can say string theory is doing this because it has both elements in it in a very natural way. In some sense, it has closed strings, so these closed Riemann surfaces, that are known to describe gravity. They are very effective to describe these kind of Calabi-Yau manifolds and other interesting spaces with specific metrics. And then we have the open strings and the branes that in a very natural way describe algebraic structures. The remarkable thing is that these are not two different aspects of string theory, but are in deep way equivalent. I will say a few words about that, but it's in some sense it's the most mysterious and the most deepest statement I think that we have found in string theory, this kind of duality between gravity and gauge theory. And it means that if you just from a mathematical point of view, the kind of object that you will in a natural way float out of closed string theory, that is the studying of loop spaces, the studying of conformal field theory, this genus expansion in terms of closed Riemann surfaces, is the left-hand side of the dictionary. The right-hand side has the typical concept that describes the open strings, which are vector bundles, K-theories, moduli spaces, non-commutative structures. And in some sense, this is our Rosetta Stone. In fact, in many ways, this program in the mathematical aspects of string theory is a reminder for those of you who are familiar with that, what's kind of has happened in the 20th century in the way geometry and number theory were connected in deep ways. And in fact, people like André Wij and others always use this metaphor of a Rosetta Stone, use this metaphor of a dictionary that kind of tries to kind of explain or connect these two different branches of mathematics. And I think what we learn here is that physics should be, string theory should be kind of the common language to connect the two. So the kind of cartoon version why this is true has to do with kind of black holes, and of course can't do justice to Maldasena's original argument, but this is the cartoon version. In a theory of gravity, we'll have black holes. Black holes are objects that have horizons, so we can naively think of this horizon as being one of the branes. We have closed strings, they describe the gravity, the curved space-time outside the black hole. And we have the open strings that, in a very naive way, you can think of as kind of being falling halfway through the horizon. That actually is a very flawed metaphor, but I want to use it anyhow. And you can think of the open strings as describing the degrees of freedom on the black hole. And general law of black hole physics says that, in some sense, this is famous motto of John Wheeler, it from bit, that in some way all the information in a quantum gravity theory, so the curvature of space-time, etc., should be encoded on the horizon of the black hole. So it should be enough just to study the degrees of freedom on the horizon, which are kind of the open string variables. So that kind of framework suggests that the two things should in a deep way be equivalent. But I think it's totally fair to say that we are still kind of very struggling to find the right kind of mathematical framework to capture this. So in some sense, in terms of mathematical beauty and what is the right way to think about geometry, I think in some sense what I would say is that at present, the right way to think about geometry is not as being the ultimate building block of nature, which might have been Einstein's favorite phrase, but more as an emergent structure. Space-time, gravity, the laws of black holes, the laws of general relativity seem to emerge out of a theory of algebraic theory, some quantum information theory perhaps. Nobody, I think, knows the full extent of it, but gravity would emerge in the same way as the laws of thermodynamics emerge out of the laws of statistical mechanics. And of course, and therefore, I mean, it's basically going back to Wheeler's point of view. If you want to have a mathematical theory that is robust, that is to say, it's very resilient against any future perturbations, it better be statistical in nature, because if it's emergent out of great complexity, in some sense, you're kind of safe. The details you'll add details, but they will never destroy the key point. Now, it's very difficult to illustrate this. I just want to illustrate with my favorite example of at least a baby version of how geometry can emerge out of algebra. And the simplest possible way is basically doing kind of brane theory in 0 dimensions, which means just having a theory of a single n by n matrix phi. In these kind of theories, you can look at the spectrum of the matrix. It's a very classical theory in random matrix theory. You look at the distribution of eigenvalues, and we know if the rank of the matrix becomes very large, then that distribution becomes a smooth function, and this was known by Wigner. And this function is actually a circle. It's a semicircle. So the eigenvalue density becomes this kind of half circle. And by taking some giant leaps here, there's a lot of details I'm just kind of ignoring, you can think of the emergence of that circle as perhaps the first example of an emergent geometry. It's a geometry that's not there if you work with finite rank matrices. But at infinite rank, certainly a natural shape, in fact a circle, could be more elementary shape, emerges. In fact, the right way to do this is in the complex setting, and then actually it's not a circle, it's actually a genus 0 Riemann surface, like over here, and you can generalize to other matrix models, and in fact, lots of other statistical mechanical models. And they have all this property that certain algebraic curves emerge. They're called usually spectral curves. So you have, in essence, the following thing. You have a system. It's a quantum mechanical system. It has a parameter, n, being the number of degrees of freedom in the system. If n is infinite, the system can be described in terms of a smooth geometry. if n is large but finite, the right way to describe it is in terms of n 1 over n correction, so you get some perturbation theory around the infinite n case, so it's a perturbation theory on top of this classical geometry. But if n is finite, like an integral over a 2 by 2 matrix, it's very difficult to see any geometry at all. So it's more like this pixelated version of this, this image downstairs. And there's like a smooth way to go from the system to this infinite system, and it's very similar as the methods in statistical mechanics. At least that's one paradigm that we are struggling with right now, and I think it's very promising. But let me just end with the two final points. So the first point I want to make is that, actually I would say that, our subject today, this kind of interaction between math and physics within string theory, I think of it as really one of the most powerful intellectual developments in the last few decades. I mean, it's absolutely stunning in terms of the depth, but it's, of course, also disappointing in many ways. So it's kind of interesting. I mentioned these examples of the early examples of mirror symmetry, etc. Now, what we have seen is that many of these results now are firmly attached to mathematical theorems. They're part of mathematics. It's very respectable to study them. But of course, in the beginning days, from a physical point of view, we always had hoped that there's a mathematical language that would help us understand and make precise the physical intuition that is, granted, is very hand-waving. So what is this space of, what is a quantum field theory? What is a quantum geometry? What is string theory? These are very basic questions. What does it mean to go in this kind of full ocean instead of staying close to shore? And the disappointing, I think, or at least at this point, it might take much longer, is that we see in some senses almost like a complementarity between the physical intuition and the mathematical rigor that's necessary to actually prove these results. And I would say there are very few cases where actually the mathematical proofs followed the same line of reasoning, the very fishy and hand-waving line of reasoning that original physical intuitions had led us, which based on some vague notion of the path integral, some ideas about duality. And I think that's still, so I hope that not only, so we've seen a lot of physics intuitions go into mathematics, but of course we do hope that in all of this, a language will emerge that actually is also able for the physics side to be captured and understood. What's the right framework to understand quantum geometry? What is a particle, what is a string, what is a brane in a true way? And I think we're really struggling here, and I think this is restoring full symmetry to this interaction, I think would be very powerful. There's another thing which is, again, lacking, is that, if you look at the field, and you look at the way I talk about it, other people talk about it, I like to use the metaphor as describing a space in terms of coordinate charts. So we have all these different topics. And we have all these dictionaries, how to relate one to the other. And they are very powerful and wonderful. And whenever we are at one of these intersections, you find a lot of fruitful research projects, beautiful theorems, a lot of progress. But there is an overarching question. What is this whole thing trying to say to us? Is there something like a way to describe this field, this object, that might very well describe reality in a more coherent way, and not in terms of coordinate charts, but in a global way? Is there something like quantum geometry? What is it? What is the language that describes the whole thing? And that in certain limiting cases then produces the topics and the examples that we know and love. That's, I would say, the mega million-dollar question. Might be too early, but I do hope, I think, in some sense, we don't lose our ambition to find these kind of language that could possibly describe this object. We know, of course, that in mathematics there are very similar research efforts, usually called programs, like the Langlands program or the whole arithmetic geometry program, that work in a very similar fashion. Many examples, a lot of unexpected, beautiful results, but still lack of a coherent single vision. But that being said, I think, so that was my last slide. I think it's a terrific subject to be active in, and thank you for your attention.
All right. Any questions for Robbert?
So, well, first, thank you. Just at an intuitive level, you showed us even twice this picture where the duality emerges as two different limits of a new world, which also might have singularities and even components that have no classical limit. But even intuitively, why just two? How does this explain duality? Why not a triality?
Oh, no. So this just, it's a cartoon. So it will have many, many ends.
But there is a thing called duality.
Yes.
And duality, as its name suggests, is duality. Whereas that picture suggests that you should have lots of different things that are sort of vaguely different limits of the same world.
Yeah, I think that's the right way to, I mean, in some sense, the grand picture is that all these various kind of limits. So duality, now what do you mean by duality? In the sense that
what
the
do
two...
you mean? You use the word.
Yeah, so what we mean here, of course, is that they're not the same theory. They're different theories. What we mean by duality is that in some sense they are, both are able to describe this kind of quantum theory. So a famous example is electric-magnetic duality, which is a gauge theory that has both electric charges and magnetic charges. The electric charges of theory 1 are the magnetic charges of theory 2 and vice versa. So then the duality means that you, and one are seen as kind of fundamental and the other ones are not. So in that case, we know these will appear at two ends because one is at strong coupling, one is at weak coupling. But your point of view that if you would look at the general case, you will have this big moduli space, it will have many, many ends. And all these ends can be used to describe, by quantization, at least a part of that moduli space. So they kind of dual in the sense, in the vague kind of physical sense of duality as an alternative description. If you think about like a pair and its dual, which are more limited, it's certainly, I think in the famous cases that we know, there are two ends. But there are famous cases of triality. In fact, it's...
But does mirror symmetry fit into that picture?
Yes, because it's like mirror symmetry would be, you have a conformal field theory and it has these kind of two chiral rings, A and B, and so the thing that you would find at the end would have a labeling, and so they would be at two different endpoints of the space. Yes. But you're quite right. So I was in no way suggesting that they always come in pairs, and I think, in fact, we know that moduli space is infinitely more complicated than that cartoon version. We have lots of branches of different dimensions, which then each of them have this whole tree-like structure. In fact, I think it's not a theorem, but there is some expectation that there's only one big space, that all of these theories are in some sense connected to each other.
Right, another question? All right. Greg.
Dangerous.
Okay.
I don't think Greg should be allowed to ask questions here.
Well, I cannot refuse it.
So is your language, your slide at the end meant to suggest that we don't have the right mathematics for quantum geometry? Or
yeah, I think that...
It just doesn't exist yet, but we have little pieces of it. Is that the message?
Yes, I would say so. I think, in some sense, I think just my observation from kind of just a mathematical point of view is that we have different concepts and even frameworks in all the different patches. They're not in a natural way related to each other. And, but this could be totally a pipe dream. There's no guaranteed reason. There should be kind of a universal set of concepts. But I would think it would be terrific if somehow string theory leads to a whole enhanced set of mathematical concepts. Don't you agree?
All right. Let's thank Robbert on this optimistic note. And there should be some coffee outside.